Hey everyone, this is our lesson on basic gas laws. And by the end of this lesson, you should be, you should be able to explain those relationships among pressure, temperature, volume, quantity of gas. And we're going to focus on the quantitative part of this for the remaining part of this unit. So we're looking at the math now. So before you get started, you may want to pause here and go back and review your gas properties. So we have a bunch of basic gas laws here. And the biggest one that you need to really make sure to know is Boyle's and probably combined, I would say. The other ones I may quiz you on, test you on just for practice so that in case you see them on the test, you're good. But these tend to be the two of the basic laws because they really focus on ideal gas law for the final exam. So let's just go over these and talk about their graphs here. So Boyle's law specifically looks at pressure and volume. So they are inversely related if the temperature is kept constant, which means it is not included in the calculation. So we've got P1 V1 is equal to P2 V2. Remember, multiplied equals inverse. Okay, and then for Charles's law, we are looking at volume and temperature when pressure is constant. So again, pressure is not included here. Volume and temperature are directly related at that constant pressure. So it's V1 over T1 is equal to V2 over T2. So remember, divided equals direct. Okay, so we've got this. I've written it at the top. It's in this yellow box down here. You should please commit that to memory. We next have Gay-Lussac's, and he is looking at pressure and temperature when volume is constant, so they are also directly related. Notice that the inversely related graph is like one of your exponential decay graphs, whereas a linear growth is your direct relationship. When one goes up, the other goes up. Now, two that you don't really need to note a graph for are combined and Avogadro's. So combined is actually looking at pressure, volume, and temperature all together. And when this is equal to a constant, you don't really have to worry about that part. But you need to know the relationships here. So we've got P1 V1 over T1 is equal to P2 V2 over T2. So if you look, we've got P1 V1 is equal to P2 V2. That's Boyle's. We've got V1 over T1 is equal to V2 over T2. That is Charles's. And then we've got P1 over T1 is equal to P2 over T2. And that is Gay-Lussac's. So that's why this is called combined gas law, because it combines all three of our basic ones here. I do want to make a note down here for this one. So this is combined gas law. You can, if you don't like dealing with fractions there, because that's a pretty big fraction, you can multiply the t's to the opposite sides and get them off the bottom. So you can also write this as P1 V1 T2 is equal to P2 V2 T1. Oh, excuse me, 1. And then the last one is Avogadro's. Remember, he's the guy with the moles, so his law should include moles. So volume and moles are directly related if pressure and temperature are constant. So that would be V1 over N1 is equal to V2 over N2. All right, so let's work through this first problem together. Again, underline what you're given, circle what you're looking for. I'm going to continue to tell you that all the time. So a sample of helium has a volume of 3 liters when the pressure is 500 torr. What volume does the gas occupy at 300 torr? So no temperature means we are looking at Boyle's law. Okay, so this is our P1 V1 is equal to P2 V2. When you know that, we can label things in our problem as well. You need to look at the pressure and volume that are written together. Okay, so these first two, volume of 3 liters when the pressure is 500 torr, those are linked together. So 500 torr would be our P1 and 3 liters would be our V1. We are given 300 torrs later in the problem, which would be P2. So that means we are looking for V2. Okay. So just kind of remember that I would very much suggest labeling everything in your problem like I just did here. Remember too that your units are the same. So pressure is both in torr. We don't have to do anything with that. So volume we're going to solve in liters. And I like to teach the box method here, which I'm sure you've heard about, in math. So we box off the unit or the variable that we're looking for, and we need to get it by itself. So we want to get that on the side of the equal sign by itself. And to do that, we are going to divide by P2 on both sides. If you prefer to plug your values in so you only see the variable left that you're looking for, you absolutely can do that. You can plug in all the numbers and then realize, oh, V2 is the one I don't have. Let me solve for that. If seeing V2 confuses you, plug in an X. That's fine. Okay, I'm not going to complain when you do that either. So now that we've divided that over, I'm going to plug in the values. So we've got 500 torr times 3 liters divided by 300 torr. We can get rid of torr and then multiply across and divide. So we've got 500 times 3 divided by 300 comes out to 5 liters. Okay. And let's make sure just logistically that this makes sense. So we know that pressure and volume are inversely related. When one goes up, the other goes down. From P1 to P2, there is a decrease in pressure, right? We went from 500 to 300. Therefore, 3 dots in a triangle mean therefore. Therefore, your V2 should be greater than your V1, because if we decrease pressure, we're going to increase volume. And it did, so that means that is an accurate answer there. So make sure, again, all your units match, and then check the answer with the inverse rule like we just did. So go ahead, pause, write this stuff down if you didn't have that so I can clear my screen. And now I want you to pause the video and try this example here at the bottom. Now, there's another example I want you to try, and I'm going to help you underline what you're given, circle what you're looking for, and label everything so that we can know where we're at. So we have 500 liters of gas in a flexible wall container prepared at 700 mmHg and 200 degrees Celsius. The gas is placed in a tank under high pressure. When the tank cools to 20 degrees Celsius, the pressure is now at 30 atmospheres. What is the volume of the gas? So we have pressure, volume, and temperature here all changing. That should tell you are looking at a law that combines all of them. Hint, hint, nudge, nudge. You need to determine that law. And we need to label P1s, P2s, all of your 1s and 2s. Okay, so do that first. Okay, so I'll make that a little note. Label 1s and 2s. And then make sure you check units. So remember, you've got degrees Celsius here. Can't have that. What do we need to change that to? Okay, so you figure that out. And then make sure to pay attention to your pressure units here. Now, they are 2 different units. So one of them is mmHg, one of them is atmospheres. I do not care which one you change to the other. You just got to make them the same. I'm not going to say make. Convert to the same. So you can do that by knowing the relationship here. So you need to know that 1 atmosphere is equal to 760 mmHg, which is stated on your reference packet in the front. Okay, so knowing this, convert one of these to atmosphere or MMHG. So pause the video, write down everything that I put here, and then try this example. All right, guys, now you should be able to calculate basic gas laws.